Okay, we're going to do this buffer problem in 3 different ways. The first thing we need to look at before we start is what buffer do we want to use? What's our acid? What's our conjugate base? So we want a pH of 7. So we first want to figure out which acid has a pKa closest to that. Well, H2PO4 minus is a pKa of 7.20. So that is going to be our base component in our buffer. The conjugate base of that is HPO4 2 minus. So that is our buffer system. So the second thing that we are going to do then is use the Henderson-Hasselbalch equation to determine the ratio of moles of the base component to the acid. So here's our Henderson-Hasselbalch equation. And again, it can be concentration ratio or mole ratio. So we're going to use the mole ratio here. So moles of our base divided by moles of our acid. So we're going to plug in then our desired pH, which is 7. And our pKa, which is 7.20, and solve for that mole ratio to see what mole ratio we want to make this buffer. And then we'll go over 3 different ways to make it with the given components or given materials. So I'm just going to use moles of base over moles of acid shorthand. So subtracting, I get negative 0.2 equals then the log of the moles of base to moles of acid ratio. So to get rid of that log, we're going to take 10 to the negative 0.20, and that gives us our moles of base to moles of acid ratio, which is 0.631. Okay, 2 sig figs keeping 1 guard digit. So this mole ratio is going to be used to calculate how to prepare the buffer in 3 different ways. So we have these sodium salts available and a strong acid and base, so we can prepare this buffer in 3 different ways as we discussed in class, and so that's what we'll be going through next. So we can directly mix the buffer component, that's one way. We can use a strong base and the acid buffer component, or we can use the strong acid and the base buffer component to make this buffer. So here's our mole ratio, right? We need to use that for all our calculations. So we're going to start by directly mixing the 2 buffer components to make this buffer. Okay, so we can directly mix the HPO4 2 minus and the H2PO4 minus to make the buffer. So looking at what is given in the problem, it tells us that we want the concentration of the conjugate acid-base pair to be 0.1 molar, and we want 1 liter of it. So this is essentially our final amount that we want in our buffer. So our final moles of acid in our buffer can be calculated by multiplying the molarity, 0.1 moles per liter, times the volume, 1 liter. So that tells us we want 0.1 moles of acid in the buffer. So that's the H2PO4 minus. Well, how much of the base do we want in the buffer? Well, we can use the mole ratio that we calculated in step B. So we know the moles of our base, HPO4 2 minus, divided by the moles of our acid, which we know we want in our buffer, 0.100, that's what the problem tells us. That equals 0.631, the mole ratio. So therefore, doing our simple multiplication, the moles of the base component we want in the buffer is 0.0631 moles. So since we have the sodium salts of the conjugate acid-base pair, and it says they're solid, we can simply just multiply the moles by the molar mass to get the mass of our buffer components. So we have our Na2HPO4. So that's where we get our HPO4 2 minus. So we multiply by the molar mass of Na2HPO4, 141.96 grams per mole. And that comes out then to 8.9 grams of the Na2, 96 grams, excuse me, of the Na2HPO4 that we want to measure out in this buffer. So same thing, or same idea with our moles of our acid component, the H2PO4. That's going to come from the NaH2PO4. So we want 0.1 moles of our acid component coming from the NaH2PO4, which has a molar mass of 119.98 grams per mole. So that comes out then to 11.9 grams, 99 grams of our NaH2PO4 to get the 0.1 moles of our acid component, the H2PO4 minus. Then of course we want 1 liter of it, so we would add water to get 1.00 liters total solution and mix that all up, and that would be our recipe for our buffer when we directly mix the two buffer components, this conjugate acid-base pair. Okay, so now we're going to look at a second way to make this buffer, and the second way we're going to make this buffer is by using the NaH2PO4, so that gives us our acid component, and sodium hydroxide, a strong base. So we can use excess NaH2PO4 and a limiting amount of the strong base, so that way that strong base gets all used up. And so we're creating the base component here. So we need to write a chemical reaction. So from the NaH2PO4, we get the H2PO4 minus. We add in a hydroxide, so we have a single arrow reaction, goes all the way to the right, and we create HPO4 minus and water. So we're going to use up the hydroxide, have an excess amount of the H2PO4 minus, so that way we create the HPO4 minus, and we have both components in our buffer. Okay, so we're going to make a mole table here. So again, we have excess acid, limiting amount of our strong base, we're creating the HPO4 minus. So again, our final moles of acid in our buffer came from the problem. 0.1 molar times 1 liter. So 0.1 molar is our final amount of our acid, which I'm going to fill in here in the table. So 0.1 moles. We want 0 of the hydroxide because it's the limiting reagent. And based on the mole ratio, like we calculated last time, or we need to calculate that based on the mole ratio like we did last time, we can figure out how much of the base component. So we have our moles of our HPO4 minus divided by 0.1 moles equals the mole ratio, 0.631. So yes, it's the same calculation as our last part of this example when we mixed the components directly. So we get 0.0631 moles of the base component in the buffer to give us the correct pH. So we're starting with 0, so that means we have to create 0.0631 moles, which means we're using up 0.0631 moles of the hydroxide and 0.0631 moles of H2PO4 minus. So obviously that means that we are starting with 0.0631 moles of the hydroxide and X amount of our H2PO4 minus. So X minus the 0.0631 equals 0.1 moles. Do our simple addition to figure out how many moles of the H2PO4 minus we want to use. 0.1631 moles. That's how much we want to mix in. Some of it's reacting, right? We have leftover excess. That's part of our buffer. So to figure out, just like the last part, we're going to multiply by the molar mass of the NaH2PO4, 119.98 grams per mole, to give us 19.6 grams of this NaH2PO4 that we're going to put in the buffer to give us the correct number of moles of the acid component at the end. So now hydroxide, we need to mix in 0.0631 moles of it, and we're using 1 molar solution, so dividing by 1 mole and then liter on the top, and then converting it to milliliters will give us then, so multiplying by 10 to the 3 mils per liter, tells us we need 63.1 mils of the 1 molar NaOH. So the third thing we need to mix in here is we want 1 liter total of the buffer. That's what we based our calculations on. So we're going to add water to get 1 liter total. So those are our 3 components we need to mix together to make this buffer. Okay, so one final way we can prep this buffer is by using a limited amount of HCl, the strong acid, and an excess amount of our base component, the HPO4 2-, which comes from our Na2HPO4. So we can again mix an excess amount of the base component, which is our Na2HPO4, which gives us our HPO4 2-, and a limited amount of the strong acid, the HCl. So just like the last prep, we have a reaction that's occurring. So here our HPO4 2- is reacting with the H3O+ from our strong acid, and it is creating the H2PO4- and water. So again, we're going to do a mole table here where we'll fill in what we know. So we're going to have excess of our base, limited amount of H3O+, and we're going to create the acid. So our initial moles are changed and our final. So again, we know our final moles of acid in the buffer. So that's going to be our 0.100 moles of our H2PO4- that'll fill in the table. So 0.100 moles. And we want 0 of our hydronium. And to figure out the amount of the base component, we're going to use that mole ratio again. So we have our moles of our HPO4 2- divided by 0.1 equals 0.631. So we know then, just like before, that our moles of HPO4 2- is equal to 0.0631, which that's what we want in our final buffer. So we'll fill in that 0.0631, just like before. Okay, so we're creating the H2PO4- from this reaction, so we start with 0, so we have to add, of course, 0.1 to create it, which means we're using up 0.1 from the hydronium and the HPO4 2-. So we start with 0.1 moles of hydronium. I'm going to say X amount of our HPO4 2-. So solving then for X, right, X is equal to 0.1. X minus 0.1, sorry, is equal to 0.0631. So X equals 1.631 moles of our HPO4 2- that we need to mix with the hydronium to make the buffer. So multiplying by that by the molar mass of our Na2HPO4, 141.96 grams per mole, gives us 23.2 grams of the Na2HPO4 that we'll put in the buffer. So then we need the 0.1 moles of hydronium, and we know that it is 1 molar solution. So dividing by the 1.00 moles, or 1.0 moles per liter, and then converting to milliliters, so multiplying by 1,000, tells us that we need 100 mils of the 0.1 molar HCl. So last component that we need, because we want a liter of this buffer, that's all these calculations are based on making a liter, so we will add water to create 1 liter total. So these were 3 different ways to prepare our buffer for a pH 7, and any of them are acceptable, but depending on what material you have available in the lab will dictate how you will prepare the buffer.